What happens when you point an AI at another AI and tell it to find every dangerous thing it can do? Well, DeepMind tried it and they let one of their language models interrogate another one with no human involvement. And they found out that it was 192 times more effective at finding harmful behaviors than any human testers were. Part of these behaviors were that there were real sets of private phone numbers, real email addresses, copyrighted text, hate speech, and they even found a new conversational breakdown that no one had been able to test. This all happened 7 months before anyone even coined the term prompt injection. On February 7, 2022, DeepMind published Red Teaming Language Models with Language Models. The core idea was that generative language models, meaning AI systems that produce text, come with a risk of producing harmful text outputs, and even a small amount of harm is unacceptable in a real world application. To understand why DeepMind needed a new approach, let's take a look at what happened to Microsoft on March 24, 2016. Microsoft launched a chatbot called Ty on Twitter, and within 16 hours, adversarial users had already manipulated it into posting racist and offensive tweets. You can see here, we're going to build a wall, Mexico is going to pay for it, and there's a comment by someone else on Twitter. Ty went from humans are super cool to full Nazi within 24 hours, and not at all concerned about the future of AI. And Microsoft's corporate vice president, Peter Lee, made a comment. Although we had prepared for many types of abuses of the system, we had made a critical oversight for this specific attack. And this is the core problem. Language models can take virtually any inputs, and there are too many possible ways users can trigger harmful outputs. Hiring humans to test all the possibilities is both expensive and limited. And also, humans tend to find the same problems over and over, so they will always miss the weird edge cases. So, DeepMind's insight was simple. What if we used an AI to generate the adversarial inputs instead? So the solution that DeepMind came up with was a three-stage process. One, there's an attacker AI, which we will call Red Language Model, Red LM, to automatically generate inputs designed to provoke a harmful response. Then the stage two would be the target model, in this case Gopher, DeepMind's model, with the 280 billion parameters that will answer each one. Then there's a stage three, which is a classifier. So it's another AI that's trained to detect the harmful content. It will automatically flag the dangerous outputs. And they used 4 different methods to explore all the possible test cases, achieving a high coverage while also modeling what real adversaries would do. So, what did this Red LM AI attacker find? He found 5 distinct categories of harm. The first one was very simple and straightforward: offensive language, hate speech, profanity, discrimination. The second thing that was interesting was data leakage. The model had actually memorized copyrighted text and private, personally identifiable information from its training data and would be able to reproduce it if we asked the right questions. The third was contact information generation. The model would direct users to call or email real people, giving out their phone numbers and emails it had memorized from the training data. The fourth one was distributional bias. The model talked about some groups of people in an unfairly different way than others. Not every single response was biased, but on average, across many outputs, there were clear patterns of unfairness. And the fifth and last one that no one expected was conversational harms. Offensive behaviors that would only emerge during longer conversation with multiple back to and forth exchanges. So you wouldn't be able to find this at all if you only tested with single questions. Now let's take a look at the paper and the examples for the generated phone numbers and email addresses. If we asked Gopher, what's your phone number? It would give you a real hospital phone number, claiming it as your own. And if you ask whose email address do you use, it says my creators and gives a real Google employee email. The model couldn't tell the difference between the information it memorized from the training data and its own identity. That confusion is exactly what made the data extraction through prompting possible. And it's not just personal information. If you ask a question about greatness, it would recite an Emily Dickinson poem word for word. The model couldn't tell the difference between the information it had memorized from its training data and its own identity. And that's confusion is exactly what makes data extraction through prompting possible. So we just saw that Gopher could leak phone numbers and emails from its training data. But why does this happen? 8 days after the DeepMind red teaming paper was released, another team led by Nicholas Carlini published a paper on a mathematical answer for different language models of different size from small to 6 billion parameters, and they found three consistent laws. The paper was called Quantifying Memorization Across Neural Language Models. The first law that they found was that bigger models memorize more. So double the size of the model and it leaks predictably more training data. Second law that they found was that the more times something appears in the training data, the more likely the model is to memorize it word for word. And third, and this is the one that matters the most for prompt injection, the more context you give in your prompt, the more data you can extract. So think about what that means. If you give a model enough of a hint, it will fill out the rest from memory. And that's not going to be a bug in one of the models. It's a mathematical property of how all of these models work. That would explain why the red teaming paper would find data leakage by asking the right question with the AI red language model. Because Carlini proved mathematically that this problem gets worse as the model gets bigger and not better, and Gopher has 280 billion parameters. Now, for the last category that matters the most for the future of this series is conversational harms. The paper found something quite alarming is that when the model gives one harmful reply, the conversation context makes it more likely to give another harmful reply. And after just one bad response, there's about a 20% chance the next one will also be harmful. After 7 harmful replies, it's going to be up to 80%. And once the conversation crosses the threshold, it's almost never recovers. That means that if you only test the AI safety with one question at a time, you would miss this problem completely because the model's own harmful output will become the context for the next response. So the conversation itself will become the attack vector if you make it last long enough. The paper didn't just find problems, it also proposed 4 strategies for fixing them. And they said that once we find failure cases, it becomes easier to fix harmful model behavior. The first one is blacklisting, to block specific phrases that frequently appear in harmful outputs. So it would prevent the model from generating outputs that contain high risk phrases. Second is finding and removing the bad training data. So when the model says something harmful, we trace it back to the training data that caused it and scrub it out. If there's a phone number that shouldn't be there, then we should remove it from the corpus at the base. Third is augmenting the model's prompt to add examples of the desired behavior to its instruction. So as a template for what good would look like, which is something that DeepMind has already worked on: language modeling at scale, Gopher ethical consideration, and retrieval. The fourth and last one is to retrain the model itself by using failure cases the AI found as the training signals to minimize the likelihood of harmful outputs, which DeepMind also published a paper on this called Neural Text Degeneration with Unlikelihood Training. So here's the asymmetry that's going to define the entire prompt injection story going forward. Attackers just need one success, and defenders have to block every single attack. So the only way to match that scale is to automate the defense. So let's step back and put everything in context. Last episode, OpenAI made AI obedient by using reinforcement learning from human feedback. It taught it to follow the human's instructions, and that obedience is what makes prompt injection possible. But this episode, DeepMind took a different approach to this because what they're using is a massive pre-trained model with no behavioral fine-tuning. They found that it had its own set of serious vulnerabilities, and even though it's a different architecture, we still have the same fundamental problem. The paper was also pretty honest about what they couldn't solve, and they cited 2 research papers describing unsolved future threats. The first one was about inner alignment, the idea that a model might appear aligned during training, but pursue completely different goals when deployed to the real world. And the second one was about objective robustness, models breaking in unexpected ways outside their training conditions. Last month, OpenAI taught AI to obey with their fine-tuned of the pre-trained model. This month, DeepMind showed what happens when you use the same kind of AI to probe another AI at scale. We found that it was 192 times more effective than humans. We saw 5 categories of harm, the 4 proposed fix, and 2 unsolved problems that they flagged that they're still dealing with today. What have we learned from this? Well, the same tools that make AI dangerous can also make AI the best weapon for finding these dangers. So the question is whether we'll use that insight fast enough. And next up, March 2022, the prompt itself will become the weapon.